Hey everybody, this next video lesson is going to cover a concept known as heat of formation. And also we'll talk about the calculations that you can do with heat of formation data. First, let's talk about what heat of formation is. Heat of formation is identified by delta H with the subscript F. It is the heat associated with making a molecule out of its most basic components. Take, for example, the molecule ethanol, which is C2H5OH. Ethanol is made up of 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom. Well, carbon comes in its elemental form as just C, so we have 2 carbons. But hydrogen doesn't come as just hydrogen. In its most basic state, it comes as diatomic hydrogen. Well, we need 6 hydrogens, so we take 3 molecules of H2. That is its most basic component. Also, oxygen comes as a diatomic molecule in its most basic component, and we only need 1 atom of oxygen, so we're going to take 1/2 of an O2 molecule. This is the chemical reaction. It's not really a chemical reaction, but it's the reaction that shows the formation of a molecule of C2H5OH. There are heats of formation data for all the molecules that are known. There's gigantic lists of them on the internet and in large volumes of books. There have been scientists who've decided or calculated how much energy it takes to create exactly 1 mole of every known substance, which is why heat of formation is not measured in just kilojoules, but often or always it's measured in kilojoules per mole because it's the amount of energy per mole of that substance. Another thing to note is that in order to obtain consistent heat of formation data, scientists have standardized the data collection process, which means that they always collect the data at the same conditions. That means that the temperature and pressure are always going to be consistent. Now, I want to have a quick conversation about the difference between standard temperature and pressure and something known as standard state conditions. Standard temperature and pressure is used with gas laws, and it is defined as 1 atmosphere of pressure and 0 degrees Celsius. Heat of formation data, on the other hand, is collected under what is known as standard state conditions. Standard state conditions are applied to anything that is involving thermodynamics, like this chapter, and also concepts of equilibrium, which we will discuss in a future video lesson. But standard state conditions and standard temperature and pressure are not the same thing. Standard state conditions is defined as 1 atmospheric pressure, but room temperature, which is defined as 25 degrees Celsius. So, oftentimes, instead of just saying the heat of formation of the ethanol is such and such, they'll say the standard heat of formation. And in order to identify that difference between just any old heat of formation and standard heat of formation, I'm going back to the delta H formation, this symbol here at the top of the screen. What we do is we put a little prime symbol in the upper right hand corner to represent standard state conditions. So anytime you see the little prime or the little 0 in the upper right hand corner of the heat of formation, we're talking about the standard heat of formation or at standard state conditions. The standard heat of formation for ethanol is negative 277 kilojoules of energy per mole. So if I wanted to create 2 moles of ethanol, well then I need to double the energy. If I wanted to create 5 moles, then I multiply the formation times 5. Heats of formation data are always known values that you always pull out of a table. You'll never need to calculate them themselves, but you will use them to do calculations for other things. But a heat of formation is a known value out of a table, and you just need to know how to use it. Here's a table of some common substances and their standard heats of formation. As you can see, it's got the little prime symbol here, and it's delta H subscript F. This is standard heat or standard enthalpy of formation at 298 Kelvin. Now, these are not all the substances with heat of formation data, but these are just some of the more common ones. You can see that heats of formation could be endothermic, meaning that in order to create these substances, energy is absorbed. For example, acetylene, C2H2, the first one on the list, is a positive number. That's an endothermic heat of formation. But some of them are exothermic. In fact, a majority of them on this table are exothermic, with only a handful being endothermic. But notice they come in either endothermic or exothermic. Now, I'm going to tell you what we're going to do with these heats of formation here in a little bit. But another note, notice that there's nothing on here that's an individual element or a diatomic molecule, because those substances exist naturally on Earth, and they don't get created, they just exist. And anything that just exists, like an atom or a diatomic molecule, has a heat of formation of exactly 0, because you can't create it, it just exists. And so there's no energy lost or gained when these are created, because you don't create them. Notice how here it also says in their natural state of matter at 298 Kelvin. At room temperature, we would expect something like sodium to be a solid, but if you ask me the heat of formation of liquid sodium or molten sodium, well, that definitely has a heat of formation. It's the amount of energy basically needed to melt it. But if in its standard state conditions, if it's in its natural state of matter, then its heat of formation is 0. Another example, imagine a diatomic molecule. Most of them are typically gases at room temperature. So nitrogen gas like N2 you'd expect to be a gas, so that has a heat of formation of 0. But what if I ask you the heat of formation of liquid nitrogen? Well, that can be looked up. That would be the amount of energy needed to make it go from a gas down to a liquid, and that has a heat of formation. The state of matter matters. If it's not what the expected natural state of matter would be, then it does have a heat of formation. Notice these are all molecules that can be created out of their component parts, their individual atoms or diatomic molecules, with one very slight variation. Check this out. Carbon in the form of diamond has a heat of formation. It's not a very large heat of formation, but it is a heat of formation. But diamond is an allotrope of carbon. Now carbon, just carbon atoms by themselves, have 0 standard heats of formation. But if you somehow create a carbon network to create a diamond, now that requires an endothermic amount of energy. And so the substance might be a pure element like carbon, and this is one of the only ones that is a pure substance like carbon, but it does have a heat of formation. But all other elements off the periodic table or diatomic molecules have a heat of formation equal to 0. We learned in a previous video lesson that heats of reaction, or delta H with a subscript Rxn, is something that we can attach to a chemical reaction that tells us whether or not the chemical reaction overall is endothermic, which means the energy is absorbed when the reaction occurs, or exothermic, which means that the energy is released when the chemical reaction occurs. Let's take, for example, ethanol. We used it in the last couple slides, so let's stick with it. Ethanol is C2H5OH, and it is a liquid at room temperature. Now let's just say it combusts with oxygen gas to produce carbon dioxide gas and water vapor. It's important to note the states of matter because remember, the states of matter affect the heats of formation of each of these individual substances. It's also important that we balance the reaction. But I don't really know the heat of the reaction. But there are a couple of different ways that we have learned now that you could calculate the heat of reaction if you don't know it. The first one we learned about back in Unit 3 in first trimester. If we know the bond enthalpy data, we could use this formula. The heat of the reaction is equal to the sum of the bonds broken minus the sum of the bonds created. But that's only if we know bond enthalpy data. Bond enthalpy is not the same as heat of formation, although they're often confused. The second way that we calculated heats of reaction was in a previous video lesson in this chapter. If we use Hess's law and we know that the elementary steps and we know the heats of each of the elementary steps, then we can add up the elementary steps to find out the overall heat of the reaction. Now the third way that you can calculate heats of reaction is by using heats of formation data. Now there is a formula just like there was for the bond enthalpy, and it looks very similar to the bond enthalpy but with slight variation. Here, take a look. You've got heat of reaction, and that's going to be equal to the sum of the heats of formation of the products times the number of moles based on the balanced chemical reaction. And then you're going to subtract the sum of the heats of formation of the reactants, also multiplied by the number of moles from the balanced chemical reaction. And if you take the sum of the products minus the sum of the reactants, you have the heat of the reaction. Notice it looks a lot like bond enthalpy, where you have bonds broken minus bonds created equals heat of reaction. Remember, bond enthalpy, though, is always a positive value. It's the amount of energy needed to break the bonds. But heats of formation may be positive or negative values because we are pulling them directly from the table. So some heats of formation are endothermic, some heats of formation are exothermic. We need to factor in that positive energy or negative energy when calculating the heat of reaction. So let's see if we can calculate the heat of reaction of the combustion of ethanol. I'm going to use table 5.3 on page 184 of our textbook. And I've taken a screenshot of it and I'll plaster it right here on the page. But you would probably want to use that table, or there's another larger table in the back of the textbook, and it lists heats of formation of a large number of different molecules. And you might want to use that in order to do your homework problems. So here's the table, 5.3, as I mentioned. And let's take a look at the formula first to remind ourselves what we're looking at. Remember, it's the heat of the reaction is equal to the enthalpy of formation of the products times the number of moles subtracted by the sum of the reactants times those number of moles. I use the table now to pull out these numbers. My products are carbon dioxide and water. And so I find carbon dioxide in its gaseous state, it's negative 393.5. But do you notice there are 2 moles of this in the balanced chemical reaction? So I need to multiply this number times 2. And I'm going to add that to the other product. Now take a look, it's water, but in its liquid state of matter. And we've got 2 different waters here. We got liquid water and water vapor. Make sure that you use the one for liquid, which is negative 285.8 kilojoules per mole times 3 moles of water. Now I add those together and I get a number of negative 1,644.4 kilojoules. That's the total amount of energy of the products. Now I'm going to subtract that from the energy of the reactants. The first reactant is ethanol, and I find ethanol, because it's alphabetical here, and it's in its liquid state at negative 277.7 kilojoules per mole. And I only have 1 mole, so I need to multiply it by 1 to get rid of the moles, because remember, heat of formation is kilojoules per mole, but heats of reaction are just in kilojoules. So the point of the mole is to cancel out the mole in the heat of formation unit. Now the other reactant is oxygen in gaseous state, and we talked about this already. Anything that's an element or diatomic molecule in its state of matter that you would expect at 298 Kelvin will be 0, and so I just add 0 moles to this. Now 1 times negative 277.7 is negative 277.7. So I take my first number and subtract my second number, and my final answer, or the heat of the reaction, is negative 1,366.7 kilojoules of total energy. Watch out here, because sometimes when kids subtract, they forget that they're subtracting a negative, and that's actually the same as adding. And so don't forget the sign matters. Subtract a negative is the same as adding. I personally was notorious for screwing up my signs back in high school. In fact, I was given the nickname the sign man by my chemistry teacher, simply for the fact that I would never remember to do the signs correctly. Here's one more example. I want you to pause the video. I've added the table for you, and I've even highlighted the ones that you're going to need so that you can find them more easily. But one that you don't see on the table is calcium chloride solid, and you would need to use the back of the textbook. I'll tell you right now that the heat of formation for this one is negative 795.8 kilojoules per mole. Pause the video now, see if you can work this out, and then hit play and watch me come up with the correct answer. So first thing we do is work on the products first. I've got 1 mole of calcium chloride, so that's 1 mole times negative 795.8 kilojoules per mole. And I'm going to add that to 1 mole of water vapor. And water vapor, if you remember, is negative 241.8 kilojoules per mole. I'm going to add those two numbers together, and I get a total of, for this side, negative 1,037.6 kilojoules. Now let's work on the reactant side. I have 1 mole of calcium oxide, and calcium oxide is negative 635.5. I add that to 2 moles of the hydrochloric acid, or hydrogen chloride, in gas form. So I take 2 moles times negative 92.30 kilojoules per mole. When I add those two numbers together, I get a total of negative 820.1 kilojoules. Now I need to take these two numbers and subtract them. Negative 1,037.6 subtract a negative 820.1 gives me a heat of reaction of negative 217.5 kilojoules, and that is the grand total energy lost for this reaction. Well, that takes care of this video lesson. Thanks for watching.